Okay, so welcome back. Yesterday, during lecture 8, we tackled two problems, a conceptual problem and, if you want, a practical problem. The conceptual problem was to calculate the distribution for an isobar, isothermal ensemble, aka the MPT ensemble, assuming the number of particles is fixed. And we use the maximum entropy principle guidelines, as we had done before, to derive the MVT ensemble. But then we tackled the problem that once we know the distribution, we don't have a practical tool to evaluate equilibrium averages if the dimensionality of the configuration spaces or in the phase space is large enough. And large enough basically means immediately, because we discussed that if you want to evaluate phase space averages by applying the definition of integral, multiplying the integrand by the volume element, even if you use slightly more sophisticated methods like Gaussian quadratures or things like that, you're hardly able to overcome just a few dimensions. And since every single coordinate comes with two degrees of freedom, you immediately see that you would be very unlikely to see any molecule equilibrium averages. So we turn our attention to the problem of sampling. And sampling means basically resorting to stochastic methods such as Monte Carlo or molecular dynamics, as we discussed. To generate configurations distributed according to our target distribution, and then use central limit theorem to evaluate arithmetic averages over this set of configurations. And the central limit theorem ensures that in the thermodynamic limit of many configurations, these arithmetic averages correspond to the phase space average that we're interested in, or to. Now, how to sample then is a practical problem, and we envision two possible ways to sample. One we did not discuss because I assumed you might have seen it at some other courses, and if this is not the case, you have to let me know. And it is the Metropolis Monte Carlo way. And the Metropolis Monte Carlo way basically generates a chain of configurations in phase space that in principle don't need to be structurally close to one another, because in Monte Carlo I can make a move, I decide how to make a move. That's called the boldness of the move. And if you average over a long Monte Carlo trajectory, you are by definition making a Monte Carlo average in terms of basically using the central limit theorem to estimate the phase space average. The alternative is to take a very long molecular dynamic simulation, which by construction will make local moves, structurally closed moves, because it displays very gently configurations. It generates a time trajectory, and this time trajectory eventually converges to the Boltzmann distribution, so in some sense you're using the ergodic assumption. Now the question is, how do we devise a Hamiltonian dynamics such that if I integrate the equations of motion, the Hamilton's equations of motion will lead to a phase space distribution density that is the canonical one, not the microcanonical one. That means that correctly samples the Boltzmann distribution. Obviously, simply applying the leapfrog algorithm wouldn't work, because the leapfrog algorithm, if in the convergent regions, which is difficult to achieve for energy conservation, will necessarily sample an isoenergetic surface, not a canonical ensemble. Okay? You might claim and invoke the equivalence of the ensembles in the large n limit, but this is dangerous for any finite number of n. Plus, keeping the energy exactly constant is a challenge numerically. Of course, there is always going to be some variation for small delta t, but it's not as straightforward as one would imagine. So we turn our attention to algorithms that have the property of converging directly to the Boltzmann distribution. And at the end of last lecture, we speculated on the idea of adding spurious degrees of freedom to couple the system to unphysical variables that more or less play the role of a piston in a gas, that can the position of a piston in a gas, which can be adjusted to generate an isothermal curve, right? So by letting the piston distance be dynamical, you can actually keep the temperature fixed. And similarly, the role of these additional degrees of freedom will be that of adjusting the velocities, or if you want, adjusting the time scales, to ensure that the kinetic energy the average kinetic energy is constantly equal to the temperature, modulo the KT factors that the equipartition theorem dictates. Okay? And now, I use the word stochastic for this sampling approach, even though the Hamiltonian dynamics is deterministic. And the reason I am entitled to use the word stochastic is that I don't have a particular way of choosing the initial condition of my system. I will have to sample that from some distribution as well. For instance, randomize the velocity according to the Maxwell's distribution. Right? So depending on what initial condition do I pick, I start from a different point in phase space. For instance, if this is the P, well, clearly, in Maxwell, the Maxwell distribution will generate some kind of bell-shaped distributions in P's, right? So when I initialize my initial condition, I will be more likely to be here than to be here in this particular case. But once I've initialized my initial condition, the Hamiltonian dynamics is in principle deterministic. Now, deterministic up to the issues associated with chaotic behavior, which of course we have already mentioned. Okay? Okay, that's it for my reviewing what we did last time. So now, let's define the Nose-Hoover thermostat. We start with Nose's Hamiltonian, Hn. Nose Hamiltonian is the physical Hamiltonian Now, I will not use capital letters or vector symbols for momenta and for positions, but I will leave that as implicit. Okay, so these are our three-dimensional vectors. Now this would be the normal Hamiltonian of my system that yields the microcanonical dynamics, right? Ensemble. It's just the Hamiltonian of the system. Now, of course, I'm going to make a modification. I'm going to add my kinetic variable S. And this S will be coupled to my physical degrees of freedom. Well, how? Well, first of all, there will be a term, G KBT logarithm of S. Where G is a coupling, which is basically the numbers of degrees of freedom. Well, this is still a decoupled system. If this was the end of it, of course, there would be, S would not be dynamical, it would just be an external field, right? It doesn't evolve. Just potential, no kinetic energy, it doesn't go anywhere, right? So let's add a kinetic energy for the S field. Q is a tunable parameter and is the mass, and I'm using, of course, inverted comma because this is not really a mass. It's not a real particle of S. Why is it a mass? Because P squared over 2m is the kinetic energy in an Hamiltonian system. But in practice, is a coupling parameter. Depending how large I choose S, then the dynamics of the S variable is faster or slower, because it's equivalent to the inertia of my S variable, right? But if I leave the system as is, the dynamic of the S variable and the dynamic of all the other variables are completely decoupled, right? There's nothing that links them, so they don't influence each other. Now, the entire building of Nose-Hoover formalism, as we shall see, consists in adding a coupling here, S, which, by the way, means that S is dimensionless, because otherwise I would screw up the dimensionality of the kinetic energy. And I think it's a square. Sorry, a square. Now, from this equation, you clearly see that the role of the S variable is that of rescaling the momenta. Since this combination is, if you want, you can imagine rescaling the velocities. If large S is large, you slow down. If S is less than 1, you speed up. Okay? Now, of course, what I need to do is to show you that this Hamiltonian yields a dynamics that ultimately breeds the right stationary distribution. And the way to do that is build the Liouville's equations for this, take the right ansatz that you want to show as a stationary distribution and show that it is a solution. Okay? But before we do that, it is convenient to switch from the original Nose formulation to the Nose-Hoover, and the contribution of Hoover was that of changing variable, basically, to make the physics of this a little bit more transparent. So what we do we introduce a new set of variables, psi equal the conjugate momentum PS divided by Q. Okay? Now, if you write the equations of motion now in terms of the psi variables and P's and Q's, what you get is the following set of equations. Q dot I equals PI over MI. P dot I equals negative gradient of U of Q. And I'm using Q1, Qn, of course. But that's not it. You also get a term, minus psi pi. Then I get psi dot is 1 over Q, sum of I going from 1 to n, pi squared over mi, negative g k b t. Now, I'm obviously skipping steps from here to here. What I would need to do is to rewrite the Hamiltonian, and then write down the Hamilton's equations, and then maybe, right? But I like this formulation better because it highlights a little bit better what psi is doing. So let's look at this. This is the Newton's equation for the nuclide, right? For the atomic nuclide. There's a force field, and there's this additional term. What kind of force is this? What kind of force is a force proportional with a negative sign to the momentum? No, that's to the position, not to the momentum. But you do have seen it in your education. Let me rewrite this in the following way. Is the force proportional to velocity? Negative of velocity. Friction. This is the structure of the friction force. In fact, you probably have all done the exercise of a parachuter in your freshman general physics course, right? That approaches a steady velocity. And what you do in that case, you just use constant friction force, constant friction coefficient, linearly depending on velocity. And this is why you burn more gas if you run fast on the highway, right? But the variable psi can take either signs. So it's a physical friction when psi is large, which basically gradually decreases velocities. But it can be a negative friction, which doesn't exist in nature, which basically corresponds to pumping up velocity into the system. And the change of psi is controlled by a term which basically considers the kinetic energy relative to some target value, number of degrees of freedom, kT. Right? So if the kinetic energy exceeds the target values controlled by the external temperature, you slow down psi. Psi dot is positive. You go towards larger values of size. Larger value of size ultimately end up positive and slow down the momentum. And vice versa. If you're below the target value of t, then you pump up velocities until you reach your target value. So this is how, in practice, the Nose-Hoover version works. It should be mentioned at this point, since you might find it in your simulations code, that this is similar to the Bernstein thermostat. So what is the Bernstein thermostat? Bernstein, I hope I spell it correctly. I haven't read it for quite some time because I'm not very much used to use it. I might misspell it, but it doesn't really matter. I hope not for Mr. Bernstein. Anyway, what is the Bernstein thermostat? The idea is very simple. You do by hand what this algorithm does dynamically. You let the system run, and every so often you rescale all the velocities to match the equipartition theorem. So it's done basically, you make, I don't know, n steps of molecular dynamic simulation. You measure the kinetic energy at the end step and set it back to 3.5 nkt and restarts. So your kinetic energy in the Bernstein thermostat would behave like, this is my kinetic energy. You start from your target value, and it will oscillate, and then zoom, it's brought back here, oscillate, brought back here, oscillate, brought back. And depending on how fast, how often you bring it back, the system, if I bring it back very often, obviously these fluctuations are all suppressed, and all I see is stable, right? Unfortunately, it has been clearly shown that the Bernstein thermostat, by construction, fulfills the equipartition theorem, but doesn't sample the Boltzmann distribution. Only heuristically approximates it. And there is no clear control parameter that says that in some limit it does it. Okay? So on the contrary, the Nose-Hoover, as we shall see now, will ultimately lead to the Boltzmann distribution, so people use the Nose-Hoover if needed, or other algorithms such as the Langevin algorithm that we will define in future lectures. Okay. So, how do we come along to show that the Nose-Hoover thermostat does the job? Well, the idea is to define an extended phase space variable. Now, for once and once only, I will write the gamma in a slightly bolder character. And then I will forget and I would use the word gamma as if it was the bold phase gamma, because I know I cannot keep a notation for too long. And this is nothing but the collection of all the Q's, all the P's, and this would be the regular gamma, but also the S, also the Xi. Well, the idea is then to write the Duville's equation in the form of a continuity equation. The Duville equation reads the following way. Now, my rho depends on all of these coordinates now, of course. And all I have to do now is to take an ansatz for rho, hopefully the Boltzmann ansatz, and show that if I insert it in here, it will solve the stationary Duville's equation. Okay? Does it make sense? Well, here's my ansatz. Now, this time, PQ, HPQ is the physical Hamiltonian, not the Hamiltonian of the extended system. Okay? Now, if I can show that this ansatz solves this equation with the term derivative equals to 0, then I'm done. Why? Because if I marginalize with respect to the Xi variable, all I get is an overall constant, which only affects the normalization. That means that I'm sampling the correct distribution. Marginalizing means I don't care what Xi is. I keep all the Xi's as they come. Okay? Well, now we'll sketch. Now, it's a matter of plug in and calculate. There is nothing conceptual from this point on. All I have to do is to set this to 0, because clearly this doesn't depend on time, and compute the gradient of this quantity. Right? Using the equations of motion. Now, if you do that, here is what comes out. Let me show you, just highlighting how calculations proceed. Well, it's instructive to look at the Duvillean operator acting on rho. Okay? Remember, the Duville's equation can be written as a Schrödinger equation in imaginary time with a Duvillean operator, which basically represents the right-hand side of this equation times rho. Well, this is negative sum over i's d by d pi's. Again, slightly improperly denoting the derivative with respect to a momentum with a partial derivative notation. This would be a gradient with respect to the pi's coordinates. Let's skip this slight abuse of notation. Over psi pi rho minus d by d psi 1 over q times pi. You can skip writing the notes here because I've put this in the notes that I'm going to deliver to you at the end of the chapter. Of course, you're welcome to write. Now, basically, all I have to show there is that this quantity is 0. Right? Well, sketching the first term, 1 gives negative sum over I, d by d pi, psi pi rho, that is equal to negative psi sum over I, 3 plus beta pi squared over mi rho. And I have to say that wherever you see rho here from this point on, I am assuming rho of the ansatz that I wrote before, which is gone. I've removed the ansatz, right? The ansatz that is the Boltzmann distribution times the Gaussian, remember? Now, this is the ansatz. So let me write rho ansatz times ansatz times ansatz times ansatz, and I want to show that if I put rho equal to rho ansatz, this is 0, right? Well, this 3 here comes from the fact that each momentum has its own component. And then I have the second term, which starts there and ends here. And the idea is to show that they cancel. Okay? Well, the second term, 2, here, yields negative d by d psi 1 over q sum. Well, that's that. And it is equal to, if you do the calculations, beta over q, psi sum over I pi squared over mi negative g k dt rho ansatz negative 1 over q sum over I pi squared over mi negative g k t times d by d psi of rho ansatz. Now, when you take rho ansatz and differentiate with respect to psi, the Gaussian factor will drop a factor psi, and surprise, surprise, you do all your calculations and you get that 1 plus 2 is equal to 0 in the sense of this notation, of course. So now finally, rho p q Boltzmann is equal integral over d psi e to the negative, rho ansatz of psi p q. Well, that's, to be honest, this is just proportional too, but you never worry about normalization when you do sampling, right? Because you compute averages. Which proves exactly what we wanted. Okay. So we now have a Hamiltonian dynamics that, if integrated properly, will sample the Boltzmann distribution. And again, yesterday, we put our hands forward to say, hey, we're not completely sure we can still use it to solve dynamics, but we'll close our eyes to this minor problem and hope that the Nose-Hoover will also be useful to study dynamics. What does it mean to study dynamics? It basically means that if I start from an initial distribution in phase space, which means I sample my initial condition from some distribution that I decide, which, for example, could be these 3 points, right? And I evolve each of them according to the Nose-Hoover dynamics. I will get these 4 points here, right? Now, if instead of 4 points I use 400 points, they will be reproducing with a statistical set an initial distribution, and I will generate 400 points in configuration space after each time interval, right? Which will represent the corresponding evolution of the distribution. Okay? So, remember, my partial derivative of my distribution is the Liouvillean times the distribution, right? And you might think about this as rho at time of gamma t being, like in quantum mechanics, e to the minus LP of rho of gamma 0. This is the evolution operator. Right? If it's working for quantum mechanics, why should it be working for Liouvillean dynamics? The math doesn't know about H1. Right? So this is a formal equation that says basically what I just depicted. If I start with an initial distribution I know, and evolve each phase point according to Liouvillean dynamics, or if you want, according to the equation of motion of Nose-Hoover thermostat, I generate a distribution for every later time. What we have proven is that the limit for t going to infinity of this distribution in the extended phase space, marginalized over the physical variable, will be proportional to the Boltzmann, the ansatz. which if you marginalize gets the Boltzmann, right? But also, we're gonna believe that this is still a good representation of the instantaneous, the marginalizing over the unphysical variable at every single time, not just at the final time, will give me a reasonable description of the instantaneous revealed phase space distribution. Right? In other words, I can solve Nose-Hoover's equation of motion and pretend it's my macromolecules equation of motion. Okay?
This is an assumption.
This is an assumption. I haven't proven it to you. And I don't think you can prove it. The idea is we have so much worse worries to worry about. That this is the moment this will be our most dramatic worry, probably we will be far more advanced than we are. Actually, this is not an argument. You agree. We need to prove it. And what people have done, for instance, say, I told you at the beginning of this course, in 2010, for instance, the group by DE Show Research performed long-time evolution. If I remember well, it was in Nose-Hoover with a thermostat coupled to it as well. I should check. And not only they were able to show that by doing this, they could see reversible folding and unfolding for a set of mini proteins that have sub-millisecond folding time. Because the relative population of folding and unfolding simply tells you that you will get the thermodynamic right, which was non-trivial given the fact that nobody had shown it with a plain molecular dynamics starting with whatever force field you have. But also the folding rates were coming up pretty much right, which tells you that the kinetics was not so far off. Now, the folding rate is one constant to describe a very complex phenomenon, right? So it's probably too much to say. But nevertheless, the fact that these dynamics will yield in the more or less right kinetics is a remarkable thing. Inexplicit solvent. Okay. Now, I'm going to say just a couple of words about the thermostat. I will not prove the thermostat because the thermostat is conceptually similar in terms of I introduce additional variables that rescale the conjugate variable of what I want to fix. And then I marginalize with respect to that, basically. But now, I want to sample the isobaric isothermal distribution, which contains a PV at the exponent, remember? Which means that I have to adjust the volume, the conjugate value of pressure, rather than the velocities, aka the kinetic energy, conjugate values of, right, that determine the temperature. Sorry, volume conjugate value of pressure, not temperature, of course. I said something. Okay, so in a very sketchy way, the idea is to introduce a simulation cell defined by three vectors that are not necessarily mutually orthogonal all the time. They can evolve with time. So I have a vector A, B, and C. And these are not unitary vectors. If I join these, I build a weird parallelepiped, not with, it's not a perfectly square one. The angles are not necessarily 90 degrees. But this is where my simulation will be. All the water and all the things will be in there. And I call H the collection of all A, B, and C. Now I'm using the vectors just to remind myself that these are in fact three-dimensional objects defining the simulation cell. And now what I do, my positions Q are given by for each I define my position in terms of the H. I can always do that, right? It's like and then I have a dynamical equation for the H coupled to the positions, so that when the H change, the simulation box adjusts, the volume adjusts in order to keep the pressure constant. And how do I keep the pressure constant? I define a pressure in terms of the Virial theorem and stress tensor, and that what makes this derivation a little bit more complicated. I don't ask you to repeat nor understand this derivation. What I want you to keep in your mind is that basically the entire idea here is to let addition of degrees of freedom compensate pressure fluctuations. Okay, so now we've reached a landmark in our course. Let me review what we did. We started from quantum mechanics, the most fundamental approach we could think of for macromolecular dynamics. We defined the idea of molecular mechanics, and by molecular mechanics I mean you take the Born-Oppenheimer approximation and you interpret the ground state energy of the electron as your potential energy for the nuclei, and you assume that the nuclei, that the electronic structure is instantaneously relaxed to the ground state, and that the nuclei evolve classically according to that potential. But then we went into a statistical physics approach because we realized that we needed that. If we want to study macromolecular dynamics, we don't know the initial conditions, we don't know the positions of all the atoms, we need a statistical approach. And by this, we arrived to two ensembles. That we know how to sample in principle. They are based on applying the leapfrog algorithm, but not to the original set of degrees of freedom, but to extended set of degrees of freedom. Okay? So we reached a landmark in the sense that now we can perform simulations knowing exactly what we're doing. Right? In principle. And I'm saying in principle because I want you to realize that this is not true in practice. But we will face that. So, from this point on, the course will bifurcate. There would be a theory part that I will take care of. And there will be a practical part that I leave entirely on you. Meaning, I will not sit down in front of a computer, download the topology, now build the you know what I mean? Sorry, download the PDB, go to this site, now build the topology by this command line, and now run the thermalization. Why don't I want to do that? Number one, time constraints. But number two, in the large language model era, you can do so much by yourself, you have no idea. To a point that I rather focus on what you cannot get from large language models from me. So I'm going to give you a set of tasks. And your task by the end of the year is to build a PowerPoint presentation or whatever presentation you have. I don't need big reports, essays, just a set of slides in which you apply the concepts that we see in class to a specific study case. And at the beginning, the task will be generate trajectories, right? And ask yourselves, have I thermalized? I will not tell you you have how to assess this. It's a question you have to figure out yourself, okay? Then when we will move on to the course and to the next chapter, which will be how to interpret the results of simulations, you will apply those concepts to the trajectories that you have generated, trying to get some insights, and revisit the concept that you have, the question that you have already asked. Have I thermalized? And then in the third phase, we will do machine learning applications to molecular dynamics simulation. We will try to address that in different positions, as we shall see, to see whether machine learning can help us tackle the problem that we have tackled with conventional methods up to that point. Does it make sense? So what do I want you to do? I list a set of tasks. 1, download the PDB structure of tetraalanine. What is tetraalanine? Is a 4-residue polypeptide made of alanine only. Why did I ask you to download alanine polypeptide? Well, I consider it a sufficiently simple system and at the same time sufficiently complex system. If I gave you dialanine, that's basically 2 alanine, and they basically have only 2 degrees of freedom. That's too simple. 3 alanine, yeah, let's do tetra. Right? So first of all, you figure out where to download it. You know you can go to the protein data bank, I'm sure. But if you don't, ChatGPT or Claude or whatever you use, or Google, how do I get the tetraalanine PDB structure? Here you go. And you find that. Not very difficult, right? You got a structure. Step 2. I asked you to install GROMACS, right? Online, look for GROMACS tutorial. There's a page devoted to the GROMACS tutorial, and in one of them, I think there's only one that I know. It shouldn't be difficult to find it. But if you cannot find it, just let me know and I figure out what it is. There's a bunch of different tutorials you can take where they guide you step by step in doing all the operation. One of them is of doing MD for canine lysozyme. Now, canine lysozyme is the dog's version of lysozyme. Lysozyme, Lysozyme, if I spell it correctly, which I never do. It's a protein that is extremely well known because it's super soluble. People have, resolved it 100 ways. We even just finished an experiment where we devised the technology to get the crystal structure of canine lysozyme from automatic experiments performed in the International Space orbiting space station. So we basically devised a small box that goes into space and operates by remotes and has all the engineering of a small lab in a box. And what we did was we produced a crystal of lysozyme, which we then sent to a synchrotron and obtained the crystal structure with very good resolution. I don't remember what it is, but in the 2 angstrom regime resolution. Why did we want to do that? Because it is believed, and we want to understand that very thoroughly, that gravity, microgravity conditions can help crystallization, because in absence of gravity, you don't have turbulent flows, which interfere with the ordered growth of crystals, so that crystals grow better in the absence of gravity. Now, this can be very useful to obtain crystals of proteins that are hard to crystallize on Earth. However, you need to be doing that efficiently, meaning inexpensively, if you want to build a space economy. Now, up to this year, to the best of my knowledge and our lab's knowledge, people have been able to crystallize lysozyme in space, but with the astronaut spending time on lysozyme. What the Zeppelin collaboration did, and I was PI of that for some time, a spokesperson rather than PI for some time, then for other reason, last year a colleague of mine took over, also because he's an expert on biochemistry. We achieved a way to do that in the absence of astronauts, so completely automatically, which is, of course, is a technical improvement. Why am I saying this? Well, there's another group that has independently achieved the same result, basically independently, and at the same time. I guess we were even on the same mission, on the same space mission. But the idea is to, first of all, show that you can do it, and in the long term, really understand whether you do it better in space. This has nothing to do with the course, but I found it cool to tell you. Anyway, that's why kyline lysozyme is very famous, because it's the hydrogen atom of protein crystallization, so to say. Now, in that tutorial, you get taught how to do some equilibrium dynamics in the native state of kyline lysozyme. Your task will be do exactly the same with a Nose-Hoover, a thermostat, and Bernstein thermostat. Follow the exact same step to run molecular dynamic simulations for tetralanine starting from a reasonable initial state that you download from the PDB. How long should you simulate? Well, I leave it to you. Don't kill your computers. Let's see how long can you go. Try overnight. Well, first try a few minutes to see what it is, and then make an estimate of how long it would be to run overnight, and see what you get overnight. Right? And save your trajectory, visualize whatever they tell you to visualize for kyline lysozyme, visualize for tetralanine. Okay? At some point, we will have a meeting, maybe in 2-3 weeks from now, where we can discuss whatever results you have obtained, so that you have any questions, we can discuss them. Okay? I'm leaving this to you because I'm sure that if you ask ChatGPT to teach you how to do that, it will do it. So there really is no point for me to spend time on that. You can do it together, you can do it separately, I don't really care, as long as you learn. Okay? Okay. I want to finish drawing that diagram to show you what lies ahead of us. Remember, at the beginning of the course, we declared 3 main challenges to be tackled for us to be able to do electrodynamic simulation. Challenge number 1 was how to get a good force field. Right? Challenge number 2, so this is the force field problem. The second problem starts from here and is the exploration problem. How to make sure that we are ergodic. Okay? But then we have our third problem, because my trajectories are large dimensional, right? And we mentioned that we have an interpretation problem, or a data analysis problem, or a data reduction problem. Okay? So being able to extract information from the big data that you've generated. So I will call this an extraction problem, or data analysis problem. And part of the reason why I want you to do your exercise is to get a feeling that even for a system as ridiculously simple as tetraalanine, these two are already considerable problems, which you can probably solve on a laptop computer. At least the exploration problem. But it's already at the borderline of what you can do on a laptop computer. But the number of degrees of freedom explodes, right? As you grow in dimensionality. And if the number of dimensions goes up, so does exponentially the number of states you have in your phase space. Right? So the exploration problem and the extraction problem will rapidly become unbearable. So what do we do, though, to overcome this? In order to do that, we will need more tools. And the tools that it turns out to be extremely useful for reasons that I cannot tell you now, because it will make an impossible challenge for me to convey why these tools are useful in the absence of any mathematical formulas. But the tool that we will use to tackle both the exploration problem and the extraction problem is to go past the Hamiltonian dynamics and consider a new form of representing the dynamics, which is not Hamiltonian, and it's called stochastic. What is a stochastic dynamics? A stochastic dynamics is, as far as our course is concerned, you can think about quantum stochastic dynamics, which is something we will not deal with. But classical stochastic dynamics are classical equations of motions, so namely Newton's equations of motion. where you have additional terms. But the additional terms are not deterministic as they are in the conventional Hamiltonian dynamics, but they are stochastic in the sense that they are random. So basically you introduce random forces and we will see how. If you introduce random forces, you pump energy into the system. You want to make sure that you don't exaggerate with the energy because you heat up the system to explosion. So you want to remove energy from the system as you add energy to the system to ensure that you get a balance. So in addition to random forces, we would like to introduce friction. So why do we want to do that? There are many ways we can motivate this approach. But before I say that, let me tell you that by doing this, I generate a distribution, an evolution for the phase-space distribution. Because I can still define the probability to find a system in a given point of phase space, right? The only point is that this distribution will not obey a Liouville's equation anymore. It will obey a slightly different equation called the Fokker-Planck equation. Okay? Why do I want to do that? Well, I can take many standpoints. One standpoint is it's just another way to treat the NTV example. Because what we will show is that you can define the friction and the random forces in an appropriate way to ensure that this stochastic dynamics ultimately samples the Boltzmann distribution. But now if you really want, you can think about this to have some physical interpretation that makes you think that maybe the dynamics you generate is not that crazy after all, as we shall see. Because the random forces can mimic, for instance, the interaction with heat bath molecules. Okay? So one practical way is yet another thermostat. Okay? But there's far more than that. The second fundamental reason for doing this is that the stochastic dynamic offers a way of dealing with the uncertainty in phase space that is stochastic from the beginning. It doesn't, because you see the ambiguity with Hamilton's dynamics is that deterministic, but then you're dealing with stochastics because we know the initial conditions are not known. So the evolution is virtually deterministic up to chaos, but the result is stochastic because of the initial conditions. So you're basically putting all the load of the stochastic behavior which you need to define a phase-space density onto the initial condition upon which you have no control. You basically define it, right? While instead the stochastic dynamics carries through the stochastic uncertainty at each step of the dynamics. This difference is key because it's so much simpler to handle mathematically stochastic processes than to handle the Hamiltonian evolution. And this will allow us to tackle very, very important quantity problems. On the one hand, it will allow us to envision enhanced sampling algorithms, for instance, for speeding up simulations efficiency, boosting simulations efficiency. Simply because stochastic dynamics is mathematically more transparent to deal with. You see what I mean by this. But there are also other more cultural rather than practical advantages. Well, to finish with the practical advantages, using stochastic dynamics, you will have a bunch of natural framework to deal with the extraction problems. Stochastic dynamics naturally leads to strategies to condense the information, which are difficult to imagine directly from Hamiltonian dynamics. Okay? So the extraction problem will be more naturally formulated, and there will be more tools that naturally emerge if you apply the stochastic dynamics. And if all this wasn't enough, there is a fourth very useful point, is that stochastic dynamics is very useful to understand fundamental points. And I want to start with one fundamental point that I will just present to you, and we will discuss next lecture in detail. All the laws of physics, well, not all the laws of physics we are interested in are invariant under time reversal. Not all, because you are aware there is something called CP violation in fundamental theory of interactions, the parity violation, CP violation of electroweak interactions, and fine, neutrinos are more left-handed than right-handed, blah, blah, blah. And since CP, T are always conserved, then if CP is violated, also T is violated. So this is not really truly always true. But let's not worry about that. At least it is certainly true for electrodynamics, okay? And strong interactions. Well, electrodynamics. So, how come we age? If the fundamental laws of physics are time reversible, how come biology is not time reversible? And I guess you all know the answer. It has a keyword, right? What is that called? Why is there a definite arrow of time if the fundamental theories, if the fundamental dynamics, the Hamiltonian dynamics, is time irreversible? Time reversible. Why? The fundamental, so the Hamiltonian dynamics is invariant under transformation t goes into minus t. And this is because the acceleration contains two time derivatives. So when you send t to minus t, the second derivative compensates the minus signs. Okay? So in a Newton's equation, there is no way to figure out whether, if I send you a set of pictures, if the pictures are going in this direction or in that direction. But if I sent you my picture when I was 30, and my picture now, I bet you can definitely tell which one came first. Right? So macroscopic laws of physics, microscopic physics behavior is not time irreversible, unfortunately. Right? And we are taught since very early in high school a key word that usually is associated with the irreversibility of time, which is called entropy, this magic word, right? I have never understood it. Meaning, I have understood that entropy grows, making energy less usable, so to say. But it's more of a mumble-jumble thing, right? Yeah, you go from an order system to a more disordered system, and it's difficult to go from a more disordered system to an ordered system. So, systems naturally evolve towards more disordered systems, and that's why you see a difference overall as time goes by, right? I would like to see, in an equation, starting from a time reversible equation, Hamilton's equation, doing a sequence of mathematical operation, and then at some point to see equation becoming irreversible. Then I have understood the origin of the arrow of time. Now it turns out that stochastic dynamics contains friction. Friction contains velocity. How many derivatives does velocity have? One, right? So that's irreversible, explaining exactly why you thermalize. You don't unthermalize, right? So the idea would be, I would start from Hamiltonian dynamics, do a set of calculations, and at some point see a friction term popping out. And that is where we will see how irreversibility emerges. And we will get an insight into this process. Okay? It's probably not something you will use in your biophysicist operation, but it's something that teaches us something about nature. And I think it's a fundamental thing.
I might have a second question about why, like aging or more generally, like the state of a system and evolving towards a certain point. Like, how can we say that is because like entropy, like why aging should be should be more entropy?
This can be, I'm not sure whether, I suspect this is a highly non-trivial question. Let me try to say. I can give a simple answer, but this is not exactly the full answer you want. What I can tell you is that, say, second principle of thermodynamics says, in any transformation, if I measure the entropy defined as the dq over t over a reversible path between the initial and final state, that grows, always, in the universe. Now, what really the second principle of thermodynamics say is all this refrigerator or thermal machine, what they can do and what they cannot do when they transfer heat. But we all know that if we translate that into entropy, it means that thermodynamical quantity grows, right? Then comes Boltzmann that says the fact that it grows, it means that it goes into a system where there are more states, equally important states available to the system, so the system can take one out of more options, and this makes the system more disordered. That's our notion of disorder. So the thermodynamic notion of entropy growth, which we associate with irreversibility, is associated with a more disordered state. And I guess we all agree on that. Now, your question becomes non-trivial when I say that this has anything to do with aging, right? Because, yes, you're telling me that entropy growth is irreversible. And aging clearly shows the signs of irreversibility. Now, you have to tell me that this is the same irreversibility. That aging is not due to some other process that yields irreversibility. Now, to be honest, I was never faced with this question, but I think, as a common physicist senses, generating irreversibility out of reversible equations of motion is an incredible challenge for a physical theory. And in fact, what we will see is that it is not true that the laws of physics really become irreversible. Irreversibility is an emergent phenomenon. The microscopic dynamics remains reversible, but the statistical behavior of it over a large number of degrees of freedom turns into being irreversible, right? Now, this kind of breaking of reversibility as an emergent behavior has been proven for entropy, and I believe the next gap is this is the only way irreversible dynamics can come from reversible dynamics, or we believe it is, right? There could be other ways. For instance, suppose the charge of the electron will change with time. As the universe expands for some mysterious reason, so does the electric charge, gets smaller and smaller. This would be another way of having explicit time dependence. But this would be an explicit time dependence that enters the laws of motion from the very beginning. It would not be an emergent phenomenon. Now, the fact that we know this emergent phenomenon led us to believe that all the irreversible processes we see in life and in the universe are associated to this phenomenon, which to some extent I agree. I'm not sure I can really prove it is the case. I only say, I use the Occam razors, if you want, and say, unless I see the need of an additional explanation, I will not give you an additional explanation. But in this sense, your question is highly non-trivial. But what we will do next lecture, we will start from the Hamiltonian dynamics and end up with the stochastic dynamics, which is an effective representation of the Hamiltonian dynamics, which is already explicitly irreversible. Now, we will deal with this irreversibility explicitly in the equations of motion, and this is why the system becomes so easy to work with at some point. Okay? Okay. I think it's time to stop. Next time I will skip the introduction and go straight into calculation. Okay? Meanwhile, if you run into problems in downloading particles, first you try to solve them among yourself. If you hit the brick wall, you tell me. Okay? Good.